Hello everyone, welcome to another kinetic tutoring episode. In this episode we're given a differential equation and we're told to find the period of the pendulum's oscillation and the length of the pendulum. So let's just get straight into the problem. Alright, the prompt reads, Jerry found the equation of motion of a simple pendulum to be d2x over dt squared is equal to negative 9x. And part A is asking us, what is the period of the pendulum's oscillation? Alright, so I'm going to walk you guys through this really simply step by step. Let's draw out our pendulum starting at a displaced position. So when the time starts, it's going to start oscillating, moving back and forth. And so the first thing we want to do is let's find a rotational displacement equation for this pendulum in terms of time. So we'll have radians, which is going to be how many radians is going to be displaced, is equal to A, which is the amplitude of the displacement. Since it's starting at an extreme, it's going to be a cosine graph, and we'll have a omega t in here. And from here, what we're going to do next is we're going to take two derivatives of this to find our angular acceleration function in terms of t. So when we take the first derivative, omega in terms of t, will get us negative a sine omega t times the derivative of the inside, which is going to be omega. And in order to find our alpha in terms of t, we're going to take another derivative, and that will give us negative a cosine omega t times the derivative of the inside again, which will leave us with omega squared. And what we realize here is that this a cosine omega t is the same thing as our displacement, so we can just replace it with theta. So we'll get that alpha t is equal to negative omega squared times theta, our displacement. And this equation that we're given actually gives us another equation for acceleration, because we know that d2x over dt squared is simply going to be a. So we'll get that a is equal to negative 9x. But since we know that our tangential acceleration, which is our a, is simply going to be our angular acceleration, we can just write this as alpha and write this as theta. And from here we can set these two equations equal to each other to find a value for our omega. So we have negative 9 theta is equal to omega squared theta. And from here it's pretty simple. Cancel out the thetas, make both sides positive, and our omega squared is equal to 9, meaning that omega is going to be plus or minus 3. Now we know that our equation for period in terms of omega is simply t is equal to 2 pi over omega. And we know that t is our period, which is in seconds, and since this value cannot be negative, the only value of omega that we can use is our positive 3, and that gives us a period of 2 pi over 3. And if we want an exact value in seconds, we're just going to plug that into our calculator, but we're just going to leave that alone for now and say that's good enough as it is. So let's move on to part B of the equation, which is asking us what is the length of this pendulum. So from here, looking at this pendulum, we're going to want to write the torque equation for the pendulum. So we know that the force that's causing the pendulum to oscillate is gravity. So let's write the torque that gravity is applying onto the pendulum. We know that our torque equation is I alpha. We'll have mg, but mg is going straight down, and only the sine component of mg is going to be affecting the pendulum's oscillation. Only that will be going in the horizontal direction, so we'll have mg sine theta. And we know that our torque is simply our force times radius, and our point mass is concentrated at a point L away from the center of rotation. So we'll multiply this by L. Our next step is going to be to divide both sides by inertia. And we know our inertia of a point mass is simply ml squared. So divide both sides by ml squared. And here's what we'll get. We can simplify this because these two masses cancel out, and this L cancels out with one of these L's. And since this is a small angle approximation, we're saying that theta is a small angle. And we know that sine of theta and theta, when we're talking about small angles, are going to be relatively similar, so we can just substitute sine theta with just theta, and we'll get that alpha is going to be g over L theta. And this looks pretty similar to our other equation here, which is alpha is equal to omega squared theta. We can kind of ignore this negative right here, because when it's oscillating, it doesn't really have a particular direction. The direction's kind of just switching around. So we can just write this as g over L theta is equal to omega squared theta. And from here we'll see that g over L, or sorry, rather omega is going to be square root of g over L. And from here, our final step is to set this equal to the omega value that we found here. Root g over L is going to be 3. Square both sides. G over L is equal to 9. And let me just erase all of this here because we don't need it. We have g over L is equal to 9. And that we'll multiply this side by L to get g is equal to 9L. And that will leave us with a L value of 9 divided by g, which is somewhere around 9.81. And our unit for this answer is going to be meters, because the length is going to be measured in meters. And this will give you somewhere around 0.9. I'm not exactly sure. You'll have to plug it into a calculator. And yeah, that's how you solve part A and part B of this problem. And thank you guys for watching, and make sure to tune in later for more physics tutorials.